Welcome to lesson number 5, Exploring Linear Functions, Introductory Explorations. Linear functions is the simplest family of functions. It's the first of our series of families of functions, so we will take it very slowly. We will stay on linear functions for about 7 lessons. So I hope over the next few lessons that you will get a good idea of what it means to say linear algebraically and what it means to say linear geometrically. By now, you've heard me mention the name René Descartes, the French mathematician and philosopher. You might know him for cogito ergo sum, which means I think, therefore I am. I am a thinking being, and since I am conscious of my thinking, I know that I exist. I am. Well, we're not in philosophy, but it's important to know that many of the mathematicians were philosophers also. He is responsible for all that we're doing today, in a sense. He changed forever the development of mathematics with the introduction of analytic geometry. He says that it came to him as in a dream. It was November 10th, 1619, so he reports. And he had a flash, a dream, very vivid, and he saw the essence of what we say today is analytic geometry. And in 2 words, that means that algebraic expressions can be represented by pairs of points plotted in the geometric plane. Or conversely, when we have a line or any graph in the plane, we can write that algebraically where the x and the y in the algebra expression represent the pairs of values which make up the points in the plane. So that's the connection. He united algebra and geometry. And it's been like that for about 300 and some years. That's what we're going to do today. So in the spirit of Descartes, we will be connecting algebra with geometry, and we will be connecting algebra with some real-life situations. More precisely, we shall 1. Examine simple linear relationships, 2. Make input-output tables for these relationships, and 3. Look at the corresponding graphs for these relationships. For our first exploration, let us go to our mathematics laboratory. Here we have a sequence of figures, geometric figures, made up of little square tiles. So you think of this as a square unit. So in our first figure, we have 2, and so on. N will be the figure number. So this is the first, second, third, fourth, and you imagine that this goes on as far out as you wish it to go. But for a pattern, 4 suffices for now. The area is the number of square units. If one of these right here is 1 square unit, then the first figure is 2. The second is 2 groups of 2 or 4. The third is 2, 4, and 6. And the fourth is 2, 4, 6, 8. Well, that's by counting them. We're in algebra here, so we want to try to come up with a formula that could give us the 10th or 15th or 100th figure with a simple formula. What we can say here is that we have 2 groups of 1, or 2 times 1. Here we have 2 groups of 2. We added 2 to the previous, so we have 2 times 1 and 2 times 2. So I can write that as 2 times 2. Over here we have 2 groups of 3. So that can be 2 times 3. And finally here we have 2 times 4. So perhaps the 10th figure would be 2 times 10. The 100th figure would be 2 times 100. We can now generalize and write our first linear equation. The algebraic or symbolic equation for what we just did is if n equals the figure number and if A is the area of each figure, A equals 2 times n. The tabular form for this relationship can be written horizontally, where in the first line you see the figure numbers, which will be our input values, 1, 2, 3, 4, and so on, to n. And our output values, which is the area, will be 2, 4, 6, 8, all the way out to 2n. In this first tabular form, where it's horizontal, we read from top to bottom, from input to output, from independent variable to dependent variable. Those are all synonymous. Or you can look at that vertically. We have a vertical table of input-output values, where in the left column we have n, which is the figure number or the input, and A, the area or the output. Again, in the left column we have 1, 2, 3, 4, and on the right column we have 2, 4, 6, 8, all the way down to 2n. This is the form that we will opt for. I prefer the vertical. You will see why in a moment, because the technology does the same. Now let us go to our mathematics technology and graph this function. And before that, let's look at the table of values that we can find, looking just like what you saw on that graphic. In column L1, you have the input values, which were the figure numbers. Figure number 1, 2, 3, 4, and 5 was not on the table, but you can imagine what that would look like. The output values, which were the areas of these figures, we had 2 square tiles, 4, 6, 8, and 10 square tiles. Ignore L3, that pertains to the following exploration. Let's plot L1 versus L2. In order to do that, we go to Stat Plot. We want L1 and L2, so let's turn plot 1 on. It was off, now it's on. So the Y will be L2, the X will be L1, or the output versus the input. We go to Zoom. Under Zoom, we have Zoom Stat that gives us the window that we need to plot those points. And there they are. Let us trace those points. At each time when that spider is flashing, or the cursor, I like to call it a spider, you have below the coordinates of the point. X equals 1, Y equals 2. This one here is X equals 2, Y equals 4, and so on. 3, 6, 4, 8, and 5, 10. These were the 5 points that we plugged in. We had 5 pairs of X, Y values. The fifth figure had an area of 10. Now, we see that those points are in a line. But what is the graph? Is it those points, or is it the line that connects them? Here are a few questions to think about. Why is this graph discrete rather than continuous? What is the equation of this line made up of 5 points, or this dotted line if you prefer? What is the equation of the connected line? It all depends on the domain that we select. The domain, remember, is the set of input values. If I just want the variable x to be the whole numbers, 1, 2, 3, 4, 5, or the natural numbers to be more specific, then we could call it n. The graph would have the equation 2n, and it would just consist of those points that we just traced. And those points would represent those figures that we saw in the algebra, and the figures in the mathematics laboratory. If now we wanted to connect those points and look at the continuous line, go from the discrete variable to the continuous variable, it would still be called 2x, but we would now use x rather than n so that x can represent all real numbers, 1 1/2, 2 1/3, everything. So they would be one on top of the other. In one case it would be just the unit points, in the other would be all of them. Let's go to the calculator and graph that continuous line and see if it goes through those points. Y equals, let's plug in the function 2x this time, and now graph And there we have it. We had the points from before, the 5 points, and now the line y equals 2x goes through them. Let's delete those points. Stat plot off, that's number 4. Now we can graph again, and we don't have those 5 particular points, but we have any point we want. Let's zoom out, meaning let's step back and look at this function with respect to the axes. So let's go to zoom out and look at here. Here's the line in the whole space. We took a bigger window, that's what we mean by zooming out, and here we have any value you want. Let's trace it and go up or down the line. Here you pick the x of your choice, and that will be the double 2 times x. That's the equation of the line. Now, of course, along the way, you have the whole numbers, but they are only some of these points. There's an infinite number of points. So every time you have an x-y pair, the y is the double of the x. Another way of looking at what we just did is we found an algebraic expression for the nth positive even number. 1 was 2, 2 was 4, the third was 6, the fourth was 8, the 10th would be 2 times 10, would be 20. Those are the even numbers starting with the first positive one, which is 2. So let's generalize. The algebraic expression for the nth positive even number is 2n. Well, we started with figures, we came up with a graph, we looked at the table, and we even now have something very useful. We have the algebraic expression for the nth even number. So what's the 20th even number? 20 times 2, 2n. What is the 40th even number? 2 times 40, so 2n is that. Let's do the same thing with odd numbers. That's what inspired me for exploration number 2. Back to our mathematics laboratory. Here we have our second series of geometric figures. Again, n is the figure number, a will be the area. The first figure has 1 square unit. The second has 1 and 2 more, which is 3. The third has 1, 2, and 2, so that's 5. And the fourth has 1, 2, 2, and 2, and that's 7. The colors help you see what has been added to the previous one to make the next one. Now, again, these are nice numbers. We actually see what they are. We know what they are. These are the odd numbers, so we're going to talk about that in a second. What I want is to come up with a formula so that I can give you the 15th or 20th or 207th figure without having to start with 1. Well, let's use what we did before to inspire us. Before we had 2, now we have a 1. Before we had 2 times 2, now we have 1 less. Before we had 2 times 3, now we have 1 less. So in a sense, compared to the previous sequence, there's a little 1 missing, so I could put this little dotted square where it was missing, right? I just showed you that. So let's do that and imagine what we had before. So over here, we had 2 times 1, but now we have 1 less. So we can write that as 2 times 1 minus 1. That's the dotted one. Here we had before 2 times 2, but now we took out 1, so we can write that 2 times 2 minus 1. Over here, we had 2 groups of 3, but now 1 is missing, so we can write 2 times 3 minus 1. And at the fourth figure, we had 4 groups of 2, and now 1 is missing, so that's 2 times 4 minus 1. Now, that means that we can generalize. I hope you understand this formula. Let's check for a minute. Does 2 times 4 minus 1 give 7? Yes. 2 times 3 minus 1, that's 5. So that works. So the nth figure, or let's start with the 10th, for example. If we had the 10th figure, it would be 2 times 10 minus 1. So we can generalize and come up with the formula a second linear expression of this lesson, and we have if n equals the figure number, and if A is the area, A equals 2 times n minus 1. Well, it's time to go back to our mathematics technology, look at these numbers, plot them, and find the line that goes through them. Again, the input value would be the n, the figure number. The output value would be the surface area. So here are the input values, or the figure numbers, first, second, third, fourth, and the fifth was not on the board, but you can imagine what that looks like. And the output values. The first figure had an area of 1, 3, 5, 7, and the next one would have been 9. We also noticed that these are the odd numbers. So they're both the areas of those figures and they're the odd numbers. Let us plot L4 versus L3, this on the output, this on the input axis, and L5 belongs to something else, so again, ignore L5. Let's go to stat plot. We want to turn on L3 and L4. That's 2. Plot 2 was off. We want to turn it on. And now we go to zoom, zoom stat as before, and there are the points. Let's trace to make sure we have the right ones. The first had an area of 1, the second an area of 3, the third an area of 5, the fourth an area of 7, and the fifth would have been 9. So here we have the points, the discrete points that correspond to those figures. These points also correspond to my first, second, third, fourth, and fifth odd number. However, we know now that we can join these points with the continuous graph. Again, going from the discrete graph to the continuous, we plug in the equation we saw was 2n minus 1, but here we're going to use 2x minus 1. It's just the name of the variable, and x usually means any real number. Let's graph that, and there we have our line. And again, if I trace, I would only get these points, so we need to delete these points so we can have our cursor trace any point we want. Let's go to stat plot, turn plots off, number 4. It's done, and now we graph. Again, let's zoom out. So let's bring us down here to about the left corner because we are in the right quadrant. We are in the first quadrant, rather. This is where x and y are positive, so I want to back up, make a bigger window so we can see the entire graph. Let's zoom out. And there we see the graph. Looks very much like the other one. The details of the intersection with the axes is coming up in one of the following lessons, so we won't worry about that now. So any point along here, if I were to trace, the y, not like before, which was 2x, but it's 2x minus 1. So you should check that. Any point where you would stop, take the x, multiply it by 2, subtract 1, and you get your y. We now have the algebraic expression, not only for that continuous line, but don't forget we have the algebraic formula for the nth odd number. And that is, the algebraic expression for the nth odd number is 2n minus 1. So that was very helpful. We had figures that were made up of tiles. We found surface area. We graphed surface area to figure number. We saw that at the same time those output numbers were the even and the odd numbers. We talked about the difference between the discrete graph, which has separate points, and the continuous graph. It all depends what story is going on, what you're interested in. If you're looking at for the odd and the even numbers, you need the discrete graph. So if I asked you, what's the 24th odd number? 2 times 24 minus 1. Well, we have 2 more explorations. They will not be geometric figures. They will be real-life experiences or real-life situations. Here's number 3. Suppose you had an electrical problem in your home, and you're somewhat of an electrician, but not a real professional one, so you need to call for help. You look into the yellow pages, and you see an ad, and this is what it looks like. Reads reasonable rates. $45 for the home visit and $25 for each hour of work at your home. Well, that looks interesting. Let's see if indeed that is a linear function. Let's go to our table board and work that out. $45 home visit, $25 an hour, the two key numbers. So your cost C for 1 hour of work would be $25 times 1 hour plus the home visit that you have to pay for. The cost for 2 hours would be 25 times 2 hours plus the home visit. The cost for 3 hours would be 25 times 3 plus 45. And the cost for 4 hours would be 25 times 4. I think you see a pattern. We'll look at those values in a moment. What's important is to see a pattern. We are now ready to generalize. We can give a formula for any number of hours x, and that is C, the cost, equals 25 times h, the number of hours, plus 45. C is the cost, h is the number of hours. If C is called y, because that's the general output variable that the calculator uses, then h would be called x, the input variable. Let us now graph the equation y equals 25x plus 45 and see what type of information the graph gives us. Y equals 25x plus 45. Let's look at the window. I have selected for you here x minimum equal to 0. That's the minimum amount of hours that he will need at your house to fix your problem. Let's hope he gets done in a maximum of 10 hours. In the y, that's the cost, $0. Actually, that should be 45, right? Because when he just comes out and it doesn't even work, you still have to pay for the home visit. And $300 is a maximum. That's probably reasonable. Let's graph the function now. And again, this is in the right quadrant, that first quadrant where everything is positive. Let's zoom out to see the line. And here we go. Now, again, everything in the negative doesn't make sense for this particular problem, but it makes sense theoretically. It's still the same equation. It's the complete equation. Let's trace and see what this gives us. Anywhere along the way, wherever you want to stop, what you read, let's stop here for example, at 5 hours of work on the x-axis, you would pay $170, which is on the y-axis. That's what this line tells us. We can read the cost versus the time. A very interesting and useful linear equation. We are now ready to explore our fourth and final linear function that also comes from a real life situation. Suppose you had a problem once and you really needed some money, and a very good friend loaned you $250. Well, what type of repayment plan will this friend require? Well, it's a good friend, so she says, forget the interest. You're lucky. An interest-free loan. And here it is. $250, and the payment plan is $18 a month. A question we could ask is, how long would it take for you to reimburse your friend? Let's look at the computation manually first. Here is your loan. We'll call that your balance that you owe, and this is your monthly payment. What will your balance be after one payment? It would be $250 minus 18 times 1, and that is $232. So you owe her less now. What is the balance after 2 payments? The original minus 18 times 2, that's 36. 250 minus 36 is 214. Let's do it one more time. What is the balance after 3 payments? 250 minus 18 times 3, that's 54. 250 minus 54 is 196. So we have here a linear equation. We're going to see that in a minute. If I call the balance the output variable, and if I call the number of payments n the input variable, 1, 2, 3, and so on, after n monthly payments, your balance will be B equals 250 minus 18n, and if B is y and n becomes x, we write y equals 250 minus 18x. But 250 minus 18x is the same thing as 250 plus negative 18x. And since addition is commutative, that gives us negative 18x plus 250. We'd like to put the x term first and the constant second. Let's go to the graphing calculator and graph that function. Y equals negative 18x plus, no, that was minus, plus 250. Let's look at the window I selected for you. We have, I started with a negative so we can see a little to the left of the vertical axis. Hopefully in 15 payments you will have reimbursed your friend. Again, I want to see a little below the horizontal axis, and 250 is the maximum amount that you owe. You do not owe more than 250. Let's graph that. Interestingly enough, we have a falling function, a line that goes downhill and not uphill like the other three. If we were to trace, look what happens. It comes up right at this number. It usually comes up in the middle of the screen. What do we read here? After 7 payments, you have a balance of $124. 7 is read on the horizontal axis and 124 on the vertical axis. An interesting question would be, for example, how many payments would I need to pay her back? Well, you would want your balance, which is read on this axis, to be 0. So that means we need to go all the way down here to see when will the graph hit the horizontal axis. When will y equal 0? I'm getting there. Here we go. 13 payments, I still owe something. After 14 payments, it becomes negative. We're going to look at the geometry of this function in the next lesson in more detail. So it's about 13 to 14 payments. One more thing I want to show you is the XY table of values. Let's go to table set. Let's set x equal to 0. That's the minimum payments you're going to make. And let's have an increment of 1 payment a month. If we look at the table, what we have here are the integer values, the XY table. Here is 1 payment, 2 payments, 3 payments, 4 payments, what I started computing on my table board. At 0 payments, I still owe the whole thing, and so on. After 1 payment, 2 payments, this is my balance. Let's go down to see if what we saw on the graph was right. After 13 payments, we owe 16, and after 14 equal payments of $18, we've overpaid by $2. We have seen 4 linear functions. Lesson recapitulation, here they are. Y equals 2n was the first. Y equals 2n minus 1 was the second. Reed's reasonable rates gave us y equals 25x plus 45. And the interest-free loan was negative 18x plus 250. The first two I put n because we started off with whole numbers. But you also saw the x because that was the continuous line. So n and x are interchangeable there. And in the last two, we could also think of the electrician working half hours and third of hours. You could also imagine giving a half a payment if you don't have the whole $18. So it's debatable. You can talk about the whole numbers. You can talk about all the real numbers. Well, in the 4 explorations, what did we do? We started with a story, or a sequence of figures, something concrete. We came up with an equation. Sometimes it was a short one, sometimes it had 2 terms. We'll look at the general one later, the general form. Then we made a table of input-output values, x in the left column, y in the right column. And then we graphed. In the first three cases, the line went up. In the fourth, the line came down. In all four cases, the graph was a straight line. In the next lesson, we're going to explore a little further the interconnectedness of the three different forms of representation: the equation, the graph, and the table.